Coding a binary heap. In the previous video, I said that a binary heap is a kind of binary tree, but in reality, that's just the visual representation. When writing code for the binary heap class, I would not use a binary tree object. I would actually use an array to store the values. And the way we can translate the heap onto the array is by simply numbering the nodes from left to right, meaning 99 would go in position 0, 94 would go in position 1, 78 in index 2, so on and so forth. Now, that being said, if all the values are stored in an array and not a node object, the question now is, how do we know what the position of a child is for any given parent node? Well, fortunately, we have a formula that can determine that for us, and that is, for any node at index x, the index of the left child will always be 2x plus 1, and the index of the right child will be 2x plus 2. Right? Feel free to pause this video for a few seconds and verify that this formula works for each parent node in the heap in front of you. Alright, now that being said, how would we implement remove max on an array? We've already discussed how that would look visually, but now let's talk about how that would look like in code. So, as we discussed, to remove the maximum value from a heap, what you do is you take the root node, which in terms of the array would be the node at index 0, and swap it with the last node, which in terms of the array would be the node at index size minus 1. So we would take those two values in the array and we would swap them. Right? Then after that, we just get rid of the last node, which in terms of the array can be done by simply decreasing the size variable by 1. Now, next step is to trickle down. Well, how would trickle down look like in an array? Well, the first step would be to take our current index, which is 0, and plug it into our formula on the left, which means that the index of our left child would be 1, and the index of the right child would be 2. The next step is to determine which side does a violation occur on, the left side, right side, or both. And after comparing, we see that a violation occurs on both sides. So, as we discussed in the first video, when a violation occurs on both sides, we're going to swap the parent node with the larger of the two values, which in this case is 94. So we're going to swap the node at index 0 with the node at index 1. Then we're going to repeat this process. So once again, our current node, the current parent node is 1. We're going to plug that into our formula, which tells us that the index of the left and right child will be 3 and 4. Right? So now we need to determine which side, if any, does a violation occur on, and we determine that a violation occurs on both sides once again. So we're going to swap 49 with the larger of the two values, which is 85, the node at index 4. So we swap. Then now we need to figure out the index of our new children. Our current parent node is at index 4, thus the indexes of the new children would be 9 and 10. So we need to determine which side, if any, does a violation occur on, and after comparing, we see that a violation only occurs at the right child, right? Index 10. So that's where the swap occurs, and thus that will complete our trickle down. Now, visually, it's easy to see why we're done trickling down. 49 has no children. However, when coding this with the array, how do we know that 49 has no children? Well, we know because when we take the current index 10 and plug it into our formula for the children, we get 21 and 22, which is clearly out of range. Our heap only has 14 nodes right now, which means that the index of the last node would be index 13. So the fact that we're getting 21 and 22 tells us that we're at the very bottom of the heap, and thus we can stop trickling down. Now, insertion. How would insertion into a binary heap look like on an array? Well, as we discussed in the previous video, the first step to inserting a value is to place that value, at the very end of the heap, or in the case of the array, at the very end of the array. And in the event that our array happens to be full when we're trying to insert, we would use the same dynamic array concept that we used for the array stack and array queue earlier this year, where we simply allocate a new array twice the size of the current array, copy all the old values, and then throw away the original array. No need to illustrate that here. For now, we're just going to focus on inserting into the heap. So we place 90 at the very last value in the heap, and then next step, now we need to determine if we need to trickle up. We need to determine if a violation is occurring, right? So we do that by comparing the value at node 14 to its parent. That being said, now it's easy to tell by looking at the heap who the parent is, but how do we know who the parent is when looking at your array? Well, once again, we're fortunate to have a formula that can determine the index of the parent at any time. And to do that, we need to learn a new function called the floor function. And here's the symbol for the floor function. And what this function means is give me the largest integer less than or equal to x. So here's how I apply the floor function to our current issue. Suppose our current child, is at node x, then the index of the parent would be x minus 1 divided by 2 applied to the floor function. Right? And fortunately, Java provides a floor function for us called math.floor. So back to our insertion, we inserted 90 at index 14, and now we need to determine the parent so we can decide if we need to trickle up or not. So when I plug 14 into my equation, I get 14 minus 1, that's 13. 13 divided by 2, I get 6.5. What's the greatest integer less than or equal to 6.5? 6. Thus, the index of the parent would be the value at index 6. We see that 90 is greater than 54, thus we need to swap. All right, now our current child index is 6, and we need to determine the new parent. Well, now we're going to take 6 and plug it into the formula. 6 minus 1 is 5. 5 divided by 2, 2.5. What's the largest integer less than or equal to 2.5? 2. So now we need to compare 90 to the value at index 2, which is 78. Once again, 90 is larger, so we swap. Now our current child index is now 2. Who's the parent? Plug 2 into the formula. 2 minus 1 is 1. 1 divided by 2, 0.5. What's the greatest integer less than or equal to 0.5? That would be 0. So now we're going to compare 90 to the value at node 0, or in other words, the root. And we see that 90 is smaller, thus no violation is occurring here, thus our insertion process ends here. So, in summary, when you're implementing remove max or remove min and you need to trickle down, the formula for determining the left child of the node at index x would be 2x plus 1, and the formula for the right child would be 2x plus 2. Then you stop trickling down either when there's no longer a violation in your heap, or the index of the child becomes greater than or equal to the size. Now for insertions, when you're inserting a node and you need to trickle up, the formula for determining the parent node is x minus 1 divided by 2 passed to the floor function. And you stop trickling up either when a violation is no longer occurring or when the child index equals 0, indicating that we're now at the root.